is visible?
Yes, sir.
Okay. So let's start the recording. So today we'll discuss about second law of thermodynamics. So can you tell me what was the statement of first law of thermodynamics? What was the statement for first law of thermodynamics? Anyone?
Sir, for a closed system undergoing a cycle, the net heat transfer to the system and the net work transfer to the system, they are both numerically same.
Okay, almost. Okay, so if you're trying to apply it for the closed system, you can say the for a
Undergoing a
cyclic,
cycle. Yes, sir.
yeah, for a cyclic process, the net heat interaction is equal to net work
Work
interaction.
trans. Yes, sir.
Yeah, so this is the applicable for the first law for a closed system, and we also applied the first law of thermodynamics for the open system. That basically gives us the steady state energy
Steady.
equation.
Yes, sir. Yes, sir.
Okay. So these are the two outcomes we know, but in general form, what we understood about the first law of thermodynamics, that is, the energy cannot be destroyed, energy cannot be generated, or energy cannot be destroyed. It can be it can be only transformed from one form to the other form. So this is the uh, basic essence behind the first law of thermodynamics. And then we applied the first law of thermodynamics for a simple system, for a simple closed system. Then we extended the first law of thermodynamics for a open system. That gives us the steady flow energy equation. So now today we'll look into the second law of thermodynamics. So what is that? So let's see. So suppose just consider one problem where you have a hot iron ball of 5 kg at 90 degrees Celsius is dropped inside a 20 kg of water container at 30 degrees Celsius. After a certain time, the system comes to equilibrium. What is the final temperature of the system? Can we solve this problem? Very easily. So we know what is the mass and what is the temperature, and also the specific heat of the iron ball and the specific heat of water is also given. So these two informations are known to us. So what I can if I apply the first law, what is the first law here? What is the statement for the first law here? That the energy lost from the ball is equal to the energy gained by the water. So that basically tells you about the conservation of energy. But there is also one assumption. What is that assumption? That the walls of the container are well insulated. That is why the water is not losing any heat in the environment. Whatever heat interaction is taking place, that is happening between the ball and the water. Is that true? So if we can apply the first law, that energy cannot be transformed, energy cannot be created, only it can transform from one body to the other body. So energy lost from the ball is equal to the energy gained by the water. So we can write that mcp, mass of iron, specific heat of iron, it should be ci, so sorry, so ci into 90 degree minus the T final temperature. Similarly, the mass of water into the specific heat of water, T final minus 90 degree. So finally, if we solve this equation and take this TF in the left side and the remaining terms in the right side, finally we'll get the TF equal to 31.57 degrees Celsius. Is it okay? Is it okay?
Yes, sir.
Okay, so basically we understood that whenever you are dropping the ball inside the water, after some time the ball will lose the heat and the remaining amount of heat will be given to the water, so the water temperature will also increase. Finally the whole system will comes to equilibrium, and that equilibrium temperature is 31.57. So there is a slight change of water temperature, and there is a big change in the ball temperature because ball has lower specific heat and lower mass, whereas the water is having higher mass and higher specific heat. So it will cause a low change of temperature of that water. So that is why we are getting 31.57 degrees Celsius. So that is basically the problem. This is very common problem. We have solved this problem in our school days, maybe in the class 9 or 8 somewhere. Okay, so this is the first heat problem in our physics textbook. So now, if I try to solve the same problem uh, in another way, can you tell me, is there any assumption to solve this problem? What are the assumptions?
Sir, actually, uh, the heat transfer only occurs between the ball and the water, no heat loss through any other
Okay, very good.
radiation or any other process.
Very good. Very good. Any other assumption? There may be assumption, there may not be. So you can say that there is no other assumption at this point of time. Let's see. Let's see. So let's try to solve the problem in another way. So the same problem, a hot ball of 5 kg at 90 degrees Celsius is dropped inside the 20 kg water container at 30 degrees Celsius. After the certain time, the system comes to equilibrium. What is the final temperature of the system? So now you can say that whenever you are dropping that ball, you you applied the first law. You said that the energy lost from the ball equal to energy gained by the water. In a reverse way, you can say there will be energy interaction. What may happen during this process, water may be start to lose the heat, and the iron ball is further can getting heated, so it can further heat it to a certain temperature. So what you are trying to write here, this part is little bit tricky, so please pay attention. The energy gained by the ball is equal to energy lost from the water. Can we write this equation? Can we write
Yes,
this
sir.
equation?
Yes, sir.
According to the first law?
Yes.
Because you are talking about energy balance. So now you are trying to say that when I drop that ball, the ball will get further heated and water will start to lose heat. Now you will take that, no, this is not going to happen. ऐसा नहीं होता है. So now you are asking that question that ऐसा नहीं होता है. Why you are saying it like this? But I am trying to say, if I say this, still it can validate the first law of thermodynamics, because first law of thermodynamics never tells you what is going to happen. It tells you that if it happen, give me the account balance. So it is basically giving you the account balance. It is trying to say that if the final temperature of the ball is 98 degrees Celsius, so there will be a 8-degree temperature rise, and the final temperature of the water will be comes down to a lower temperature. Finally you can find out the final temperature of the water body will reach to 28.78 degrees Celsius. So if I try to solve this problem, you can check that still I am using the first law of thermodynamics here for energy balance. So you can tell from this example that in the previous example you have one assumption. What is that assumption? Whenever you solve that problem in the
টেম্পারেচার ফ্লোটা হায়ার টেম্পারেচার থেকে লোয়ার টেম্পারেচারের দিকে হবে।
exactly, so you have one assumption that you consider it is very much obvious, but who told you that this is obvious? So that is a question that you told it that the heat transfer will happen from high temperature to low temperature. Okay, very good. So is it always true? Is it
Yes,
always
sir.
true?
Yes, sir.
Always true. So now, if you think about a summer afternoon, so your surrounding is extremely heated at 45 degree or 44 degree Celsius. Okay. Now simply you switch on the AC. So what will happen? After some time, the room temperature will start to drop and the heat is being transferred from the room to the surrounding. Whereas your room is at low temperature and the surrounding is at high temperature. Still you are getting a transfer of heat from a low temperature body to a high temperature body.
Yes, sir. True.
বাট স্যার সেখানে স্যার আমাদের
এটা
একটা
তো কোনো যে
পাওয়ার
ন্যাচারাল
ইনপুট
প্রসেস
দিতে
না।
হচ্ছে, একটা
Natural
মেকানিক্যাল আমাদের
process. So yeah,
ন্যাচারাল নয়। হ্যাঁ
true. So there will be a correction in the previous statement that in a spontaneous manner, heat flows from a high temperature to a low temperature body. That you are trying to say. But whenever you are making some external effort, in that case you can get a reverse way. But in naturally means spontaneously, you always get heat transfer from a high temperature body to a low temperature body. So this was the assumption whenever you are solving the problem, and you never thought of that. You thought that only the first law is required. No, you are also required one assumption. That assumption is heat flows from high temperature to low temperature body in a spontaneous manner. So how we got this assumption? Let's try to understand what is the mathematics behind this assumption. So let's try to see. So second law, so what I'm trying to say, that first law talks about the, if the process happens, what is going to happen to the initial state and the end state. So if the process happens, then what will be the final temperature? The first law can talks about this kind of information, but the second law tells you that the process will happen or not. Is it going to happen or not? So basically the second law talks about the probability of a process, probability of occurring of a process, that if a process is going to happen or not, that is going to, that we can find out from the second law, that this process is feasible or not. Just like I'm giving one example, just it will be further. Suppose if I show you one video, is it clear to you?
Yes, sir.
Okay, so this is one video. Okay, and the next video is this one.
স্যার একজন না জয়েন করতে চাইছে।
Okay, so if we see these two processes, now tell me that which one is forward and which one is backward.
Breaking the glass is forward. That means the first bit.
So
First one.
yeah, so now what I'm trying to say, that if you can say this, that this one is the forward process and the next one is the backward process, that means these intuitions that by which you are saying this is forward and this is backward, it basically from the second law of thermodynamics. The second law of thermodynamics tells you that the second process cannot happen. You got my point? So in natural way, just like heat cannot be transferred from a low temperature body to high temperature body, just like that one is true. Similarly, some small fragments of glass pieces, they cannot accumulate and form a glass and cannot move upward direction. So this intuition is also stated by the second law of thermodynamics. So the second law of thermodynamics tells us the direction of the video, or maybe the arrows of time. Suppose you are watching one video, suppose someone played that video reverse. So after watching 2 or 3 seconds, you told that, oh, this is the wrong video, so you are playing it backward direction. So the sense you are using to find out that the movie is moving forward or backward, it is basically by the second law of thermodynamics. So you already have that sense that what is second law of thermodynamics. So second law of thermodynamics talks about a feasibility of a process. You got my point? So I'll just explain it further. So if I note down that the first law of thermodynamics talks about the quality of energy, quantity of energy, that how much quantity of heat will be transferred or not. Second law of thermodynamics, which asserts that the process occur in a certain direction. It basically gives us of a direction of a process. Suppose I'm just giving one example, that suppose you have a container that contains some amount of hydrogen gas and another container that contains some amount of oxygen gas. If you mix two gases, what is going to happen? That can be determined by the second law of thermodynamics. Are they going to react and form H2O vapor, or are they not going to react and they are simply diffuse into each other? That can be determined by the second law of thermodynamics. So it basically tells you that which process is going to happen, and there will be some mathematics of that. I will go into that. The second law of thermodynamics is more about the quality of the energy. It talks about the quality, like what is quality, that thing. And what is the main statement of the second law? It states that your first law told that energy is conserved. It can be only transformed from one form to the other form. The second law states that as the energy is transferred and transformed more and more, the quality of the energy degraded. As the energy transferred or transformed from more and more, the quality of the energy is going to degrade. So we have to understand what is the quality and what do we mean by degradation. So these things we will discuss. So I'm trying to mainly trying to summarize that the first law is basically about the balances. So it balances that in which direction what is going to happen. And the second law talks about the direction of the process, like which direction is feasible and which direction is not feasible. And the first law is going to say about that if this happens, what is going to happen? If this happens, so before applying the first law, you need the know that what is going to happen at the end. And from the first law, you can finally find out what will be the end states. So that I will discuss. Just wait. Before that, we have to understand that what is called heat engine. So heat engine is basically a device. It absorbs heat from a high temperature. It converts some part of the heat into work, and remaining amount of heat it rejects in the environment. So this is basically the 3-step. Okay. Now, I told you in the first class, in the beginning class, that what was the objective of thermodynamics, studying thermodynamics. I told you in the first class that the main objective is that we have huge amount of thermal energy in the earth. So basically we need to convert this thermal energy into mechanical energy. So that the mechanical energy can be used for improving the quality of human life. Just like think about that. In the old days, for irrigation, we have to based on some human labor. But as we were moving forward, what we are doing, we are using machines. These machines needs electricity. This electricity is basically generated in some thermal power plant. So, or maybe for irrigation, we need tractors. Those tractors are basically runs by the chemical energy of fuel. That chemical energy is converted into thermal energy, and that causes some motion, and by using that motion you obtain work. So basically we need mechanical work. So heat engine is basically a device that converts thermal energy into mechanical energy. So these are the main objective of heat engine. So for heat engine, what was the first four things? It absorbs heat from a high temperature source. Secondly, it converts heat into work. There will be some remaining heat that will be rejected in the environment, and it will operate on a cycle. So it will be a continuous process. It's not like that. It is a one cycle, one go. It's not like a one go thing. It will operate continuously. So every time it will absorb heat, the heat into work. Every time it will reject some of the heat in the reservoir, cold reservoir, and it will operate on a cycle. So these are the main feature of a heat engine. So now, to characterize the performance of the heat engine, we have one parameter that is basically called efficiency. So what is efficiency? I will discuss that later. But at this point of time, we have to understand that what is heat engine, what is happening inside this. What is happening inside this heat engine? It is absorbing the heat from a high temperature body. So just understand that suppose you are burning some coal. As you are burning some coal, it is generating a hot flame, and from that hot flame you are running a boiler. Okay, so you are absorbing the heat from the burning of coal, and finally you are driving a steam turbine from that steam. So that is generating the mechanical energy, and finally you are rejecting the remaining heat in the condenser. So that condenser heat is basically finally going to some near about pond or near about river. That hot water is continuously transformed there. So this is basically the heat engine. So if I want to closely see what is happening inside, so what is happening inside there, you can consider, I am giving one example. So it is basically example. There are several form of heat engine. So just like whatever inside your car, that is basically your heat engine. A power plant, that is also a heat engine. So what it does, there is a boiler. In the boiler you are absorb the heat from a furnace. The furnace is basically having some the coal. You are burning that coal in presence of air, that is generating some heat, and that heat is basically transferred to the boiler. And after that boiler, there are water tubes. Water tubes, basically the water pipes. These water tubes finally absorb that heat and finally convert into steam. This steam has high pressure and high temperature. This steam is finally heating the turbine blades. I told you in the initial class, these are our main objective, that these turbine blades, the steam is impinging on the turbine blades. Due to that, these turbine blades will start to rotate, and that will create a electrical flux cut inside the generator, and finally you can get some electricity. And the remaining steam will come there, and finally there is a condenser. What is condenser? Condenser is basically, it transforms vapor into liquid. So whenever you are transferring vapor into liquid, you need to reject that heat. So there will be some atmosphere. In the atmosphere, it will reject the heat. Or maybe there is a cooling water circuit. Some cooling water circuit is there, and it is passing like this. So whenever that cooling water coming to that part, the steam rejects that heat to the cooling water. And finally, the steam convert into liquid water. And again, further you pump this liquid water and pressurize to that level, and then you further heat it inside the boiler. So this process is continuously happening. And finally, you are consuming some work in the pump, and finally you are producing some work, that is basically in the turbine. So your net work output is equal to W out minus W in. Okay. So this is your net work output. So this much amount of energy you have converted into useful form, and this is the energy that you have finally supplied as in the form of fuel. So similarly, this cycle is also present in your car. In the IC engine, you are supplying some chemical energy. That chemical energy is basically finally burning and creating some piston motion, and finally there is a exhaust. so through which you are rejecting that heat in the environment. So everywhere the same cycle is operating, be it a nuclear power plant, be it a thermal power plant, or the power stations. Similarly, there can be a gas turbine power plant, what is happening in the aeroplane. There can be IC engines. Everyone, these are the examples of the heat engine. So if I try to summarize what is heat engine is basically a collection of devices that form a cycle, and it absorbs heat from a high temperature source and convert into useful work. And we know that we need work. Okay, so this is basically a input output device where input is your thermal energy, output is equal to mechanical work. So this is the heat engine. Any doubt up to this much? Any doubt? Hello? Am I audible?
Yes, sir.
Yeah, I can hear you. Can you hear me? Okay. Yeah. So if I am repeating this thing from the first class because it is very important for you, that if I try to understand what is happening inside a heat engine, if I try to understand what is happening inside a heat engine, in heat engine in a gross manner, there is a heat input, there is a heat output, and there is some work output. So these are the three components of a heat engine. But if you try to understand closely that what is happening inside this cycle, that is basically magnified here. Here you can see that there is basically boiler. In the boiler there are some water tubes, basically some pipes that are carrying water. This water is absorbing heat from some burning of coal. So that coal is burning, and finally it is generating a huge flame. From this huge flame you are absorbing that heat and converting that water into steam, and the temperature and the pressure of steam is very high. Now this steam jet, now this steam become a jet, and this steam jet hits on the turbine impeller. Turbine is basically having some blades just like your fan, just like you have your stand fan. Similarly, in the turbine there are some layers of your stand fans. So if you heat that turbine, and those fans are mounted in a single shaft. So if this steam jet hits on the turbine, so the main shaft will start to rotate. If this main shaft start to rotate, it will also rotate those coils. That is basically your electrical concept that will cause a flux cut inside the generator, and finally you can get electricity. But the out of steam, which is finally reduce its pressure and comes to condenser. Whenever it comes to condenser, it will reject the heat. Okay, so after rejecting the heat, it will again convert into liquid, and that liquid is again pumped and finally reach to high pressure and further feed into boiler. So this cycle is continuously operating. Okay, and by final the net work output will be the turbine input, turbine output minus the pump input, because pump is absorbing some energy, but the fraction of energy absorbed by the pump is less than 0.1%. But the main is basically the output. So this is the output and this is the input. So that is why we have to define one parameter that is basically called the thermal efficiency. Thermal efficiency represents the magnitude of the energy wasted in order to complete the cycle. So whenever, or maybe it is basically written in the negative form, you can say that how much energy it is basically utilized during this conversion. So if you have Q amount of energy, suppose 100 joule, now you have converted 80 joule of thermal energy into work. So you have successfully converted 80%, and remaining 20% you are not able to convert into form of work. It basically again remain as a form of heat. So suppose you have 100 unit of thermal energy, you have tried to convert into work. finally you will find that you have only converted 80%. Still you have 20% heat that you are unable to convert into work. So the efficiency of that engine will be 80%. You are not wasting any energy. The energy is basically not being converted into work. So energy is still balanced. If you are trying to apply the first law, you will check that the energy is still balanced. So it is basically the performance of that engine. So just like that, suppose you are trying to buy one car, that car is giving a mileage of suppose 15 kilometer per liter, and another car which is giving you 25 kilometer per liter. So you can definitely say the heat engine inside that car is much better than the previous one. So it is basically the performance index of a engine. So just like that, we can define this as a desired output by the required input. So if I try to put what is my desired output, what is my desired output? So what is my desired output?
Turbine work.
The turbine work, or maybe you can say the network. Okay,
Network.
because there might be some work input. So if you try to say that it is the main work output, that is a W, and what is the required input, how much you are paying for and what you are getting. So you are
Q1.
paying for the fuel, and finally you are getting
input.
the so basically the Q in is your required input, and the Q out, that one you never thought about. Suddenly you got it Q out. Q out, the amount of heat that you are rejecting, that you never desired for. You always wanted to that value should goes to 0. So your desire is that how much I will supply heat. I will try to convert this heat completely into work. That was your desire, but in reality that doesn't happen. So for a heat engine, the desired result is that the net work done and the input of the heat supply to make the cycle to operate. So this is the thermal efficiency. So if I try to apply some first law, what I can write that from first law, I know that if it is a cycle, I can write down that my W net equal to Q in minus Q out. Is that right? Cyclic integral of heat equal to cyclic integral of work. So cyclic integral of work equal to W net, and cyclic integral of heat equal to Q in minus Q out. Why there is a minus? Why there is a minus? Why there is a minus?
The heat flows from the system to the environment.
Very good. Because heat rejection from the system is always defined as a negative sign. And whenever you are supplying heat to the system, that is defined as a positive. So the net heat transfer, whenever you are talking about net heat transfer, you have to consider the sign. Just like here, if I try to apply it for the turbine compressor system, my W turbine minus W pump, because my W net I can write down that is nothing but my W turbine minus W pump. Why it is so? Because W net is basically work done by the system. So by the system, this is by the system, and this is on the system. As it is on the system, that is why there is a negative. Similarly, it is the heat that is basically transferred to the system, and this is the heat that is basically transferred from the system. As there is a form, that is why there is a minus. Okay, so anyway, so if I try to define my efficiency, so efficiency is eta thermal equal to W net out by Q in. So W net out, you can write it like Q in minus Q out by W in, Q in. So finally your efficiency can be written as like this. Is that right? Now I have one question, that how we can increase the efficiency? How we can increase the efficiency of a thermal heat engine?
By decreasing the value of
By
Q
reducing
out.
Q out. Yes.
By decreasing the value of Q out. So if we reject the, if we can make this Q out equal to 0, my thermal efficiency will be 100%. So now what happened, that now I'll explain the second law of thermodynamics. The second law of thermodynamics says that that is basically called as Kelvin Planck statement for heat engine. What Kelvin Planck say, that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. That is basically the statement of second law. What is the statement of second law? They are saying that it is impossible for any device. So it is basically talking about an engine that operates on a cycle. It received heat from a single reservoir. So it cannot operate absorbing heat from a single reservoir and produce work. It must interact with two reservoirs from which it will absorb a heat, and from the other, into the other, it will reject the heat. So interacting with a single reservoir is not possible. It must interact with two reservoirs. From one reservoir it will absorb the heat, and in other reservoir it will reject the heat. So basically it is trying to say that this Q out, try to remove the complexity of the language. Mathematically it is trying to say this Q out cannot goes to 0. It will be always non-zero value. Theoretically it is not possible. You got my point? Now the question that comes to your mind, that why? If I do some ideal process, from that ideal process I can make it 0. No, it's not like, it's not about the ideal. For ideal process also you can't get it 0, cannot get it 0. So why it is so, I will explain. But before that, so if I try to summarize the first law and second law, first law tells you that the thermodynamics says that the efficiency of heat engine cannot be greater than 1. What is the meaning of that? The efficiency of heat engine cannot be greater than 1. Why it is so?
The conservation of energy statement.
Exactly. So if you are paying for 100 rupees and finally you are getting the product of 150, it is not possible. Whatever you apply coupon. But if you are paying for 100, you can get for only 100. Amazon and Flipkart, they may try to fool you, but finally you never get a product which is having a price higher than the higher than the thing that you are paying. So it will always lesser. So it is trying to say that if you pay for 100 joule, you cannot get it 150 joule. Okay. Similarly, for the second law is trying to say that the second law of thermodynamics said that the efficiency of a heat engine can never be equal to 1. So it is trying to say that the first law says that it cannot be greater than 1, and the second law says that it is always less than 1, because you are not allowed to convert heat into work completely in a cyclic process. I am repeating my statement. Conversion of heat into work 100% theoretically is not possible in a cyclic process. Is it true? Why? Let's see. So just consider this cylinder piston. If we consider this cylinder, it is having some gas at 30 degrees Celsius, and you are putting one load. Now, if we bring this piston cylinder in front of a reservoir which is having a temperature 100 degrees Celsius, and if you supply 100 kilojoule of heat, what is going to happen? If we supply heat from this reservoir 100 kilojoule, first thing will happen, the gas temperature will increase. If the gas temperature increases, what will happen?
Sir, can you repeat the example from the beginning?
You have one piston and one cylinder, and in this piston cylinder you placed one load. This load is having a weight W. So now the initial temperature of the gas is 30 degrees Celsius. If you place one reservoir at 100 degrees Celsius and allowed a heat transfer, so what will happen? It will transfer heat from a high temperature to low temperature. It is a spontaneous process. And suppose you consider that 100 kilojoule of heat is being transferred. Very good. So if we supply this heat to this gas, what is going to happen? The gas temperature is going to increase. So as the gas temperature will increase, the temperature will become, suppose, 90 degrees Celsius. But due to this temperature rise, also the gas expanded. Due to that, finally you are see one expansion, and this expansion cause the lifting of this weight, and this lifting of weight is basically some weight into some displacement. So this will lead to some work output. Suppose this work output is 15 kilojoule. Is it acceptable what I have said? These two processes are acceptable. Is it okay?
Yes, sir.
So
Yes,
you
sir.
have so you have supplied some heat, the gas temperature increases. Due to this increment, the gas expanded, and due to that the weight is also pushed some upward direction. That is why it performed some work. Very good. So basically, suppose you consider that this is my heat engine. So suppose you have some books. Okay. Now you are trying to, your parents are saying that take this book and put it over the bookshelf. So what you have done, you bring one stove. By this stove, you are heating one piston cylinder and placing those books over this piston. So if we heat that stove for a long time, what will happen? That the gas will expand, and finally the book will change its position. It will lift from a lower position to higher position, and finally from that you are transferring it from the bookshelf. So you are not doing any kind of energy. You are saving your energy for your future work. So you are trying to convert the thermal energy or the chemical energy of your gas stove into mechanical energy. But the problem is that whenever you want to repeat the cycle, so again you want to add some weight, and again you have to heat it. So whenever this system is at 90 degree and your heat source is 100 degrees Celsius, after some time they will come to equilibrium. So there will be no heat transfer. So for again heat transfer, you have to bring it back to this 30 degree. Then only you can continue the cycle. So you started from one process, you reach to the other state, and if you come back again, then only the cycle will happen. Then only you can further put some weight and raise it to a certain level. So that is why the gas needs to be bring down to again to the initial temperature. For that, you need a low temperature reservoir, and that low temperature reservoir is at 20 degrees Celsius, and the gas temperature is at 30 degrees Celsius. So the gas will spontaneously reject the heat. How much heat it will reject? It will reject 85 kilojoule. Why? Because you supplied 100 kilojoule, it performs some work with 15 kilojoule, and the remaining heat, it will again transfer 85 kilojoule. So basically this 85 kilojoule of heat is not converted into work form of energy. So you can say it is basically a form of waste. So finally useful, you have converted 15 kilojoule. Now after that, the gas is again brought to the initial state. Now you can again repeat the cycle. Again you supply some heat, the gas temperature will rise, it will cause a rise of the load, and by which you can get some mechanical energy. Again you have to reject the heat and bring back to the initial state. So this is the way you can say that the efficiency of my device is now 15 is the work output divided by the 100. So it is basically the 15%. So that gives you the justification that we cannot convert heat into work completely in a continuous manner. So whenever you are trying to bring the system to the initial state, you must reject the heat. Basically, you have to understand that whenever you are supplying this heat, this heat is causing some random motion of these molecules. As there is a random molecule of the motion, some part of the motion is basically in the upward direction. The remaining part of the motion is basically diverging in different direction. Those energies are waste energies. Those energies are basically random energies. From that energy, you cannot do some useful thing. But only a part of that is hitting this plate, which is doing the useful part. And those random motion is not contributing to anything. That is only increasing the internal energy. But if this complete internal energy can be organized in a specific direction, then you can get the 100% conversion. But in practical, it is not possible, because we know that from the ideal gas assumption, whenever you add some energy to the molecule, it creates random motions. So, but some part of that random motion is basically creating some part of the vertical, a unidirectional motion. That is basically causing this weight lifting. So you can say that if you add 100 joule energy or 100 kilojoule energy, what is happening? Basically, the 85% of that energy is moving in random direction. Only 15% of that energy is basically contributing in this direction. That is why you are getting a lifting of this weight. So this is basically tells you that we cannot make this Q out. We cannot make this Q out to a zero. There will be always a heat rejection. So this much I want to discuss. So if I try to say that the energy can be classified into majorly two forms. One form is called the high grade energy. One form is called the low grade energy. High grade energy means electrical work, the mechanical work. Those are basically the useful energy, what we need. And the low grade is basically the heat energy, the internal energy or the chemical energy. These are basically the form of energy that may not be required by us. So these are available energy in the earth. So if we think about a conversion from high grade means mechanical work. Suppose you have mechanical work. If you try to convert this mechanical work into low grade energy, that means basically heat. This conversion is possible and 100% is possible. But whenever you have some low grade energy, basically form of heat, and you are trying to transfer this heat into work, this conversion continuously 100% is not possible. So there is a theoretical barrier, there is a physics barrier. That barrier tells you that this conversion is not possible. It is not about some ideal process, whatever ideal process you assume, but theoretically even it is not possible. So that is why we are studying this thermodynamics subject, so that we can maximum convert this, so that our efficiency increases. So efficiency cannot be zero. There will be a theoretical limit of the efficiency. And now we have to achieve the efficiency to that level so that we can hit the maximum theoretical level. but the maximum theoretical level is not 100%. It is less than 100%, and it is governed by the Carnot efficiency. You already know about that. 1 minus TL by TH. You heard about that in your class 12 physics, that the theoretical limit of this conversion is directed by the Carnot limit, that is the 1 minus TL by TH. Okay, so this is the main discussion for this today. If you have any doubt, I can clarify it. So there are some processes. These are basically called the spontaneous processes and non-spontaneous processes. So the second law talks about the spontaneous process and which one is non-spontaneous process. So those things I will discuss in the next class. So when we'll discuss about the entropy. So if you have any doubt, you can ask me.
স্যার, যে কোনো একটা প্র্যাকটিক্যাল প্রসেস রান করতে গেলে সবসময় কিছু না কিছু লস থাকবেই, বাট আমরা যদি দুটো প্রসেসকে মানে কম্পেয়ার করি, একটা প্রসেসে ফর্ম অফ এনার্জিটা চেঞ্জ হচ্ছে, মানে মেকানিক্যাল থেকে ইলেকট্রিক্যাল বা ইলেকট্রিক্যাল থেকে মেকানিক্যাল হচ্ছে, আর একটা প্রসেসে ফর্ম অফ এনার্জি চেঞ্জ হচ্ছে না, বাট প্রসেসটা রান করছে। তো এই দুটো কেসের মধ্যে কোনটাতে লসের পরিমাণ বেশি মানে হবে, এটা কি কম্প্যারিজন করা যায় কোনো?
Acha, if I give you one example is just you consider that suppose you have one hydraulic turbine. Have you heard about the hydraulic turbine? Those turbine is basically some
জলের প্রেসারে টারবাইনটা ঘুরছে।
Okay, so have you seen wind turbine?
Yes.
Wind turbine, those long fields where you have some fans like those things, and those things rotates. So if you consider one wind turbine, so what is happening in the wind turbine? You are supplying some kinetic energy, so that is basically the kinetic energy of wind, and finally that kinetic energy is transferred in the wind turbine, and that wind turbine is converting into electricity. So now the question is that what is the form of kinetic energy? Is it a high grade energy or low grade energy? Wind energy, it is a high grade or low grade, or mechanical energy or heat form of energy?
মেকানিক্যাল এনার্জি।
Mechanical energy. Okay, and finally so whenever you are getting the turbine motion, and that is basically causing some electricity generation, that is basically also the electrical form of energy. So basically you are converting between thermal, is basically you are converting between mechanical to electrical. You have to understand these two things is happening inside the same bracket, high grade energy. So you are converting high grade to high grade. Is that right? Now
Yes, sir.
I am trying to say during this conversion, theoretically 100% is possible. But what is the actual efficiency of wind turbine? Around 70%, 75%, 80%. But this value was 60% 10 years before. If you go 20 years forward, the efficiency of wind turbine can reach to 99.99%. Theoretically and practically, because you are trying to reduce the frictions, all those things you are trying to remove so that you can increase the efficiency. Your theoretical limit is 100%, because I told you the conversion of high grade to high grade 100% is possible. Now what I am trying to say, if you consider the reverse one, suppose you have one IC engine where you are supplying fuel is basically some petrol or diesel, and finally you are getting some mechanical motion. Now if we try to do a balance, you will see the efficiency will come to around 35 to 40%. Now if we try to remove the friction, if you are trying to make the process ideal, everything trying to make it ideal, finally will reach to a efficiency that is 45%. Maybe if you reach to 200 years forward, in maybe 2200, you can see you have the same engine with a 60% efficiency, because there is a theoretical barrier, you cannot cross it. Have you got my point?
ওকে স্যার, মানে আমি অ্যাকচুয়ালি এই পয়েন্টটা বলেছিলাম, তার কারণ হচ্ছে ট্রান্সফরমারে তো ইলেকট্রিক্যাল এনার্জিতেই কনভার্ট হচ্ছে, জাস্ট স্টেপ
Exactly.
ডাউন বা স্টেপ আপ। সেই ক্ষেত্রে আমরা 96% 97% এফিসিয়েন্সি
Exactly.
করতে পারি, বা কিন্তু মোটর বা জেনারেটরের ক্ষেত্রে অত ভালো এফিসিয়েন্সি পাওয়া যায় না। মানে সেই জন্যই আমার এই কোয়েশ্চেনটা মাথায় এসেছিল যে
Exactly. না, মোটরের ক্ষেত্রে তুমি যদি বলো মোটরে কি হচ্ছে, তুমি ইলেকট্রিক্যাল এনার্জি পাঠাচ্ছ, সেটা মেকানিক্যাল এনার্জি তৈরি হচ্ছে। এই
Yes,
মোটরের
sir.
হ্যাঁ, তাহলে এই মোটরের মধ্যে যে কনভার্সনটা সেটাও কিন্তু তোমার মানে হাই গ্রেড টু হাই গ্রেড, মানে সেম সেম ক্লাসের মধ্যেই। এখানেও কিন্তু থিওরিটিক্যালি 100%-এর কাছাকাছি পাওয়া উচিত, কিন্তু সেখানে এডি কারেন্ট লস থাকে, আরো কিছু লসেস থাকে, তার জন্য হয় না। কিন্তু দিস এফিসিয়েন্সি ইজ ভেরি হাই, অ্যারাউন্ড 85%, অ্যারাউন্ড 80%।
মানে
আমি ওটাই বলছি।
আপগ্রেডেশন করা গেলে ওটাও 99 টু
হ্যাঁ,
98 এরকম রেঞ্জে যাওয়া যেতে পারে।
যাওয়া যেতে পারে, বাট ইফ ইউ
আচ্ছা।
থিঙ্ক অ্যাবাউট এ আইসি ইঞ্জিন, যেখানে তুমি ইউ আর সাপ্লাইং হিট এনার্জি অ্যান্ড ট্রাইং টু কনভার্ট ইনটু, ইউ আর সাপ্লাইং লো গ্রেড এনার্জি অ্যান্ড ট্রাইং টু কনভার্ট ইনটু হাই গ্রেড এনার্জি, যদি তুমি এটা কনভার্ট করতে চাও, তুমি কখনোই কার্নট এফিসিয়েন্সির বেশি পৌঁছাতে পারবে না। অ্যান্ড
ওকে স্যার।
কার্নট এফিসিয়েন্সিটা লিমিট হচ্ছে হাই ডিফারেন্স। তো সেই কারণেই আমাদের একটা মানে আইসি ইঞ্জিনের এফিসিয়েন্সি এখনো কিন্তু 40% থেকে 35%। একটা বেস্ট গ্যাস টারবাইন প্ল্যান্ট ওয়ার্ল্ডের মধ্যে তার এফিসিয়েন্সি হচ্ছে 60% অনলি। সো এই কনভার্সনটা ফ্রম থার্মাল টু ইলেকট্রিক্যাল অর থার্মাল টু মেকানিক্যাল, এটা প্রচন্ড প্রচন্ড ডিফিকাল্ট আর কি। ইট ইজ নট এ স্পন্টেনিয়াস প্রসেস, ইউ হ্যাভ টু পে ফর ইট। তো এইটা হচ্ছে মেন সামারি, ক্লাসের সামারি আর কি।
ওকে
So now in the next section we are going to look into how this efficiency can be increased and কি করে আমরা ইনক্রিজ করতে পারি, সেটার জন্য আমাদের এই পুরো সাবজেক্টটা পড়া, এবং কোন কোন ফ্যাক্টর থাকে যেটা এফিসিয়েন্সিটাকে কমিয়ে দেয়। During high grade to low grade energy conversion, does all the molecules move in specific manner? I don't know. For whenever you are trying to get low grade energy, during that time you don't need any kind of specific motion, because low grade energy is basically form of heat, and this heat does not depend upon motion. So when you have heat, when you have a high grade energy, that needs a specific motion. But whenever you are talking about low grade energy, this low grade energy is basically form of heat, and this does not relate with any kind of mechanical motion. And those molecular motion, random molecular motion, can never go আমাদের হাই গ্রেড টু লো গ্রেডে মলিকুলার মোশনের স্পেসিফিক ডাইরেকশনটা দরকার নেই।
ওকে স্যার।
বোঝা গেছে আমি কি মানে উত্তরটা ঠিক দিলাম? বোঝা গেল?
হ্যাঁ হ্যাঁ স্যার বুঝতে পেরেছি।
ওকে, সো এই বিষয়টা প্রচন্ড ইন্টারেস্টিং আর কি, মানে আমি প্রথমবার পড়ে আমার প্রচন্ড ইন্টারেস্টিং লেগেছিল। তো ইউ ক্যান ওয়াচ সাম ভিডিও, ইউটিউব ভিডিও, দোজ থিংস when we'll take next class. Okay, so yeah, I can take on Tuesday 29th. 29th is okay for you?
থার্সডে।
Thursday? Thursday? No, Thursday একটু ডিফিকাল্ট হবে আমার জন্য। আমি থার্সডে ক্লাস নেব না, আর আমি আপ টু 5th ক্লাস নেব না, আমি একটু আউট অফ স্টেশন থাকবো। সো আমার 29টাই লাস্ট ক্লাস হবে।
স্যার 29 স্যার 29 হলে এই সন্ধ্যে হয়ে যাবে একটু।
হ্যাঁ হ্যাঁ, কোনো অসুবিধা নেই।
ঠিক আছে স্যার।
7টা 8টা 9টা তোমরা যখন বলবে, যখন সবার সুবিধা হবে তখন আমি নিতে পারি, আমার কোনো অসুবিধা নেই। তোমাদের অ্যাভেলেবিলিটি ওয়াইজ আমি নেব, আমার দিকে কোনো রেস্ট্রিকশন নেই আর কি।
ওকে স্যার।
তোমরা দেখে কথা বলে নাও একটু কখন হবে, কিন্তু আমি থার্সডে নিতে পারবো না, কারণ থার্সডেই রাত্রেবেলা আমি বেরিয়ে যাচ্ছি আর কি। তো সেই কারণে একটু চাপে থাকবো আর কি। ফর আর নেক্সট উইকটাও ক্লাস থাকবে না। তো আমি অ্যাসাইনমেন্ট গুলো দিয়ে যাব, লোকজন অ্যাসাইনমেন্ট গুলো সলভ করতে থাকুক সেকেন্ড লটা শেষ করে, দেন উইল মিট। আমি ফিরে এলে তারপর আবার ওই সলিউশন গুলো চেক করে দিই, কারেকশন গুলো করে দেবো।
আচ্ছা
ঠিক আছে, ওকে, তাহলে আমি অফ করছি তাহলে আজকের জন্য।